So these equations describe an atmosphere in radiative equilibrium, yet the dependencies in frequencies render the problem formidable to solve. In practice, we're dealing with infinite equations with an infinite set of equations, one for each monochromatic frequency. Now, because of that, a very stringent but sometimes useful approach is the gray approximation, where we're going to drop the dependency on frequency. We're going to assume that the opacity does not depend on wavelength. Now, under this admittedly very limited condition, we can simply integrate the radiative transfer equation in frequency, and these three equations simply become, well, the first one is the same because the first one was defined in terms of the bolometric flux. Now, for the second equation, if the opacity does not depend on frequency, then you can take the opacity out of the integrand and the opacity cancels, and you have that the frequency integrated mean intensity is equal to the frequency integrated source function. And finally, for the last equation, if you have that the opacity does not depend on the frequency, then what you have is a relation between the pressure, the frequency integrated pressure, the gray opacity, the gray optical depth, and now the frequency integrated flux, which by the first equation is a constant. So you can easily integrate this equation and find that the pressure is related to this constant flux times the opacity over the speed of light plus a constant. That's simply integrating this equation. So that set of the three equations that actually, the last one is a set of infinite equations, become in this gray approximation a set of three very simple equalities. The flux is constant, the source function is the mean intensity, and the pressure is the optical depth. These equations are so simple that it makes sense to look for situations where an atmosphere can be treated in the gray approximation.